Hello everyone, and welcome to the session number 9 of this lecture series entitled EXO in Structural Engineering. In the previous session, we started working on a dynamic graph that shows the ductility status of the beam under consideration. The graph was defined in terms of the ductility parameter, epsilon t, and the strength reduction factor phi. After creating our zones and the boundary between these zones, we defined a point that will represent the ductility status of the beam with coordinates of epsilon t and phi, the actual epsilon t and phi values for the beam under consideration. Let's plot that point on the same graph and try different beam ductility scenarios by changing the input parameters related to the steel reinforcement diameter in order to check our Excel template for correctness. I'm going to use the mouse to select the chart that we created in the previous session. I'm going to right click, then select data, and I'm going to add a new series. The new series will consist actually of one point. For the x-axis, I'm going to use this value here for epsilon t. For the y-axis, I'm going to use this value here for phi. Once I click OK, you can see that the point that we want is actually displayed here, which is quite small in terms of marker, so I'm just going to double click on it and try to increase the marker a bit, let's say size 6 points, so that it will be clearly visible. And I'm going to close this. There we go. You can see that the point is actually a bit far from the arrangement that we created in the previous session. Let's try to understand why. If we go back here to sheet number 1, we will see that the beam that we are studying is actually a beam that has the dimensions of 300 width by 600 total depth. So this is quite a big beam. But in terms of reinforcement, we have 5 bars, 12 millimeters in diameter. If we check the actual reinforcement area, we will see that it is 565.48 millimeters square, while the minimum area allowed by the code is 529. So this here is a very lightly reinforced cross section. That's why the point that we have just created to indicate the status in terms of ductility of the beam is very far from the arrangement that we created. So if we go back to sheet number 1 and we try to reduce the total depth of the beam a little bit and try to increase the amount of reinforcement, let's say here 22 by 22, click back on sheet number 2 and you will see that the dynamic graph will immediately and automatically change the information. Now your point is located closer to the arrangement that we have created, but we are still in the tension controlled zone. Let's add some more steel. Let's say here we're going to have 25 and 25. Oops, you immediately see here the alarming red color indicating that you have a problem. Immediately once you click on sheet 2, you will see that we have jumped into the transition zone. So the beam is unacceptable according to the code. If we try to further increase the amount of steel reinforcement, let's say 30 by 30, again we will see here from the alarming color that you have a problem. But when you click on sheet number 2, you will see that you have jumped into the compression controlled zone. Now if we define a lightly reinforced cross section, let's say 18 by 18, and let's say that we want this line here to stretch all the way to reach this point, which gives us an indication about the ductility of the beam that we are studying. We can do that through defining the benchmark endpoint here. This point here is actually defined on this line here. So what we can do is we can actually tell Excel to extend this line all the way to the location where this point is at. But there's a problem there. When the section is tension controlled, this line will be stretched to reach this point here. But if this point is actually in the transition or in the compression controlled zones, then this line will actually try to stretch in the opposite direction. Therefore, we need to use an if statement in this case to tell Excel what to do and to always put us in the right scenario. So we're going to come here and tell Excel if this value B8 is actually greater than B4 plus B3, if this value here is to the right of this benchmark endpoint here, then stretch this line all the way to the point in orange. So I'm going to say if B8, which is the value of epsilon t, is greater than B4 and B3, which is the location of the benchmark endpoint here, as we've defined it here, then in this case, the benchmark endpoint X value will be nothing but this point. Otherwise, if this point is in the transition or in the compression controlled zones, then we do not want the line to stretch in the other direction, and we want this point here to remain as B4 plus B3. So I'm going to tell him if the if statement is not satisfied, then just use B3 plus B4. Let's try it. I'm going to click enter. You will see immediately that Excel has stretched this line to reach the point that you have created. If you further reduce the amount of steel reinforcement, let's say 16 by 16, you will see that the line will further stretch with the point that you have created. And in case you increase the steel reinforcement, let's say to 25 and 25, so that we will fall in the transition zone, then this line here will remain exactly as it was before introducing this point, and the point will dynamically be moved to represent the correct ductility status of the beam. Next, I want to move this chart into a new sheet and hide sheet number 2. The user has nothing to do with sheet number 2. The information here will be automatically reflected in the chart, and the information here will be automatically updated when the user changes the input parameters. So the first step here is that I'm going to click on the chart and right click, select move chart. Let's move it into a new sheet. Let's call this sheet phi chart. Click OK. And the chart will be moved into a new sheet. Next, I want to hide sheet number 2. So I'm going to click on sheet number 2 here and right click and select hide. Now we have a sheet called calculate, where all the calculations are made, and a sheet is called phi chart, where the results of the ductility parameters are shown graphically. I want to fix this chart a little bit by adding a title to it and adding titles to the x-axis and to the y-axis. So let's do that. I'm going to go from here to design, add a chart title. I'm going to call this chart strength reduction factor phi. I'm just going to copy that and define the same thing for the axes titles. So let's say for the vertical primary, I'm just going to add the same title here, and for the x-axis I'm going to insert strain in steel farthest from the neutral axis. I'm going to select everything and fix the font here. Oops. Here, let's say 12. And here we have the same thing, 12. And here, I'm going to make the title bold. And let's say 16. There you have it. Now the chart is ready. Whenever you go to the calculate sheet and change your input parameters, let's say here I'm going to have 600, you can go directly to the phi chart and see that you are in the tension controlled zone. Once you have created this chart, you can actually go back and forth between the chart and the sheet where the calculations are made and play a little bit, change the input parameters, study different scenarios for different beams, and make sure that your EXO template is actually working correctly. We need to perform one more step in order to have this EXO template fully functional and readily available for use. If you remember in previous sessions, this sheet here, which we called today calculate, used to be sheet 1. And in one of the previous sessions, we actually protected sheet 1 against any changes that might be made by the user. If the user now, after protection, tries to change any of the text here, tries to move this figure, for example, the user cannot actually do that because this sheet here is protected. You remember we went to review and we actually protected the sheet. Now it says here unprotect because this sheet is already protected. So if we click here, you actually have to enter the password, which we defined as 1234, in order to unprotect this sheet because this sheet has been already protected, and the user now can do nothing except for change the input parameters. The user cannot change any of the other cells here. The user cannot move this chart. The user cannot see the formulas in the output parameters region because we have hidden them. All this took place after we actually prevented the user from making changes by actually protecting this sheet. Okay, in today's session we have created a new chart and we hid a sheet called sheet number 2. I don't want the user to be able to do any changes to the entire worksheet that we have created. In order to do so, I'm gonna click here on protect workbook, not protect sheet. You can go here and tell EXO to protect this sheet in particular, but since we have now different sheets and I have a hidden sheet as well, I can tell EXO to protect this workbook by inserting a password. Let's say we're going to use the same password, which is 1234. Click OK. Let's re-enter it, 1234. Again, try always to use rigorous passwords, but I'm just doing this now for illustration. Okay, and now the entire workbook is protected such that the user can actually use this template but cannot inflict changes, especially unwanted changes, to it. I'm going to hide the toolbar here, increase the size of the template to 100%. Now this sheet is ready and this chart is ready as well. This session concludes a series of 9 sessions created to help you understand how to develop an EXO template to be used for the analysis of rectangular, singly reinforced concrete beam cross sections for flexural capacity. I would like to thank you for your patience and congratulate you in the case that you have fully implemented the procedure described in these sessions to create your own Excel templates with the structural engineering applications. Please stay tuned to this channel where I will be creating more sessions with interesting and even more challenging Excel templates. Best wishes to all of you.